Hi and welcome. In this video we're going to look at a second example out of section 14.2 and 14.3 on partial derivatives, and this is a second example about the application of partial derivatives to business and economics. Okay, so in this example we have the total cost of producing 1 unit of a product is given by C of xy is equal to 40 plus 4x plus 6y plus x squared y over $100, where x represents the cost per pound of raw materials and y represents the cost per hour of labor. So y represents the cost per hour for labor. Now, in our first example, when we talked about the profit function, our x value represented the number of units of a product. In that case, it was the number of pounds of kisses, and y represents the number of units of a second product. In our example, it was the number of pounds of creams. In this case, our x value and our y value do not represent the number of units of different products. So when we get to the point where we're interpreting our partial derivatives, we're going to need to think a little bit carefully about that because we don't have sort of that template from the first example. Okay, so in our first part of the example, we are going to be asked if raw materials currently cost $35 per pound and labor wages are set at $15 per hour, how much will it cost to produce 1 unit of our product? Okay. Now, a second observation here is that unlike the joint cost function that we would have if x and y represented the number of units of two different products, in this case, the output is not the cost to produce x units of something plus y and y units of something else. In this case, our cost function is strictly about 1 unit of the product being produced. So our input is the cost of the raw materials and the hourly cost of labor. And those two pieces of information inform us about the cost to produce 1 unit of our company's product. Now, if you wanted to ask the question of, well, what would the cost be for many units? Well, then we would take this value and maybe multiply it times the number of units of some product. But in this case, we're focusing on the cost to produce 1 unit of our product. Okay, so we have our formula for our cost to produce 1 unit, and we can plug in 35 for x because x represents the cost of the raw materials, and 15 for y because y represents our hourly labor cost. And so we do that, we plug it all in, we type it into the calculator, and hopefully, you should double check this, we get a final output answer of 453.75. And because we're talking about cost and we're measuring that cost in dollars, our final answer is $453.75. So it will cost the company $453.75 to produce 1 unit of this product that this company is producing. Okay, so the next question that we want to ask about is, we would like to know, all right, all of our cost information right now is based off of the cost of the raw materials and the cost per hour for labor. And so what we'd like to know is, if either of those two costs is increased, how will that affect the cost to produce 1 unit of our product? Another way to think about that is, if the company knows that either the cost of raw materials could go up, perhaps from tariffs, or the cost of labor could go up, perhaps because minimum wage is being raised, what is the company's best interest? Do they want to hold down the cost of raw materials, or do they want to try and hold down the labor costs? Okay, so to answer this question, what we're going to be asking is, we are going to be looking at our partial derivative with respect to x and our partial derivative with respect to y. So we'll calculate our partial derivatives, and then we will evaluate both of them based on the current raw material costs of $35 per pound and the current labor costs of $15 per hour. Okay, so we are now ready to calculate some partial derivatives. So I'm going to start by rewriting the function down. Our cost function is 40 plus 4x plus 6y plus x squared y over 100. And before I go and I take my partial derivative, for me it's kind of nice to maybe take a look at that last term here, this x squared y over 100. Because that 100 is in the denominator, I might have to do something complicated to take that derivative. Or I can rewrite this term. And the way that I can rewrite this term is by pushing that 100 to the front of the x squared y. And if I do that, it's a number in front of the x squared y, but it's in the denominator, so I need to make sure that I have a placeholder in the numerator. So when I rewrite this function, I have 40 plus 4x plus 6y plus, and then when I push that 100 to the front, I have 1 over 100 x squared times y. Okay, so now that I've rewritten this function, then the next thing that I want to think about is my partial derivative with respect to x. And every time I find a partial derivative, I want to set my mind so that in this case, our variable is x and y is considered a number. So x is a variable and y is a number. And so now I am ready to calculate my partial derivative. So looking at my cost function, my derivative of 40 is going to be 0. And then I have my plus sign. And x is our variable, so I have the 4 times x. So I carry along the 4, and I take the derivative of x, which is 1, so I didn't even write it down. Then I have a plus sign. And now I have 6y. The 6 and the y are both numbers, so when I have a number sitting by itself, its derivative is 0. Okay. And then I have another plus sign. And for my last term, I have the 1 over 100 is a number, and the y is a number, and there's an x squared in the middle. So whenever I have a mixed term, I carry along the numbers, and I take the derivative of the part, in this case, that has the x, the variable involved. So in this case, I'm taking the derivative of the x squared. So I have 1 over 100. The derivative of x squared is 2x. And then I carry along the y. Okay, so now we've found our partial derivative of c with respect to x, and I might clean that up a little, but I certainly don't need to write the zeros in there. And when I look at 1 over 100 times 2, I can multiply those together and I get 0.02. So my cleaned up version of the partial derivative of c with respect to x is 4 plus 0.02 xy. Okay, so now we are ready to, hey, my computer is going crazy. Okay, back that one up. Okay, so we are now looking at the partial derivative of c with respect to y, and now I want to shift gears, and I want to think about y as being the variable and x as a number. So when I look back at my original function, my cost function over here at the beginning, every time I see a y, I want to think of y as the variable. Every time I see an x, I want to think of x as a number. So when I take the derivative of the 40, I get 0. My derivative of 4x, well, there's no y's in there, so 4x is a number sitting by itself, so its derivative is 0. My next term, after the plus sign, is 6y, so I can take the derivative of the y and carry along the 6. So I carry along the 6, I write that down. My derivative of y will be 1, so I don't even need to write that 1, and I end up with 6. Okay, so now I'm on to the last term, and the last term is 1 over 100 x squared y. So the 1 over 100x squared is my number part, and so I can carry along all of those pieces. And when I take the derivative of the y, I get 1. And so now I have my partial derivative of c with respect to y. And I probably want to clean this up a little bit, and when I clean this up, I end up with 6 plus 0.01x squared. The 1 over 100 is the same as 0.01. I'm going to go ahead and write that as a decimal. Okay, so now we have both of our partial derivatives, and our job is to find the two partial derivatives and evaluate both for the current raw material cost of $35 per pound and the current labor cost of $15 per hour. So for each of these partial derivatives, we now want to plug in an x value of 35 because the raw material is our x value, and 15 for the y value because our y represents the current labor cost. I will say in one of your remote assignments, or one of the problems in your remote assignments, that the x and the y might not necessarily line up with this problem, so be really careful that you're plugging in the right numbers for the right variables because every single problem can be a little bit different. Okay, so here we have our partial derivatives on our new page, our partial derivative with respect to x, our partial derivative with respect to y, and we're going to plug in our x value of 35 and our y value of 15, and once we do all of that, we end up with 14.5. Cool. We're going to do the same thing for our partial derivative with respect to y. We're going to plug in our x value of 35 and our y value of 15. And when we do that, crunch some numbers, we end up with 18.25. You should double check those numbers, make sure that you agree with those numbers when you type those into your calculator. Okay, so in our instructions, we are asked to find our partial derivatives, evaluate them at the current cost values of $35 per pound, per pound, and $15 per hour. All right, so let's interpret our partial derivative of c with respect to x. So our c is our cost to produce 1 unit. X represents the cost per pound of raw materials. And so when we're thinking about this 14.5, we're saying that that is a change in cost by increasing the raw material cost. So think carefully about that. There's a lot of words like cost and dollars going on here. Okay. When we increase our raw material cost by $1, we will increase the cost to produce a unit of our product by $14.50. So here's our summary. If raw material costs are increased by $1 from $35 per pound to $36 per pound, but labor costs remain the same, then the cost to produce 1 unit of our company's product will increase by approximately $14.50. All right. So, for example, if tariffs are put into place and your raw materials go up by $1 per pound, then the cost to produce 1 unit of your product is going to go up by $14.50. Okay. So that's our interpretation of the partial derivative of c with respect to x. Our partial derivative of c with respect to y, well, that's going to tell us about how an increase in the cost of labor is going to increase the cost to produce our product. Okay. So if labor costs increase from $15 per hour to $16 per hour, and raw material costs remain constant, then the cost to produce 1 unit of our company's product will increase by approximately $18.25. Okay, so if, let's say, minimum wage is raised from $15 per hour to $16 per hour, how will that affect the cost to produce 1 unit of your company's product? The answer is it's going to increase the cost to produce 1 unit of your company's product by $18.25. All right, so when I look at these numbers, I can see that what's my goal here? If I'm talking about profit, I want to have a bigger increase, but when I'm talking about cost, I want to increase the cost to produce my product by less if I can, because I do not want to have my costs increasing a lot. So for the company's benefit, if one of these two initial costs has to be raised, either the cost of raw materials or the cost of labor, I think I would prefer for my company to have the cost of raw materials increased, because in that case, we only raise the cost to produce the product by $14.50, as opposed to increasing the cost to produce the product by $18.25 if we raise labor rates. So here's our summary. The company will want to prioritize keeping labor costs down, because an increase in labor costs will cause a greater increase in production costs to the company. All right. Thanks for listening.